Good morning, afternoon, evening, TCAP Bio, whatever time you're watching this. This is the first presentation for Domain 4. There's 7 of these. I've broken it up into smaller chunks. The musical guest for Domain 1, not Domain 4, is a little Eminem, one of my favorite artists. This is Survival, which is the clean version. His little song, a little bit kind of relating back to Natural Selection. So anyways. Okay, I'll get back to that. So sorry. So we're gonna start with evolution first. And we talk about evolution, we talk about natural selection. Why I'm starting with natural selection first is because those of you that took biology last year, we did not get through all natural selection. So we're going to start with this first because it is the foundation for all biology. Darwin, talk about him a little bit. I got my Darwin bobblehead right here. But when we talk about natural selection, we talk about Darwin. Now, there were other folks before Darwin that actually had ideas that there was a change occurring. And so the first one we had Lyell, which was geology. Let me move my mug down here a little bit. He had this idea of uniformitarianism, that the Earth was very old. During pre-Darwin time and even before Lyell, people thought the Earth was a set age, nothing ever changed. And so these individuals really kind of upended a lot of scientific thought at the time. Malthus was this idea of exponential population growth. So exponential growth is a J curve. And so what that is saying is that populations will continue to grow, right, if there's no kind of competition, those kind of things. And then Lamarck, evolution, but he had this idea of acquired characteristics, which is wrong. Still evolutionary, but this idea of acquired characteristics is this idea that you can acquire a trait now and it'll be passed on to your offspring. So Lamarck's idea was, one of his evidence was like, if a bird kept doing this, like a duck, it would form webbing. We know that doesn't happen. Also, Lamarck did a lot with, like, one of the Lamarckian things is giraffes. The giraffes kept stretching their necks got longer. So we talk about Darwin again. You don't see much on the AP exam about his voyage, but what happened was Darwin kind of was at first probably a failure in the eyes of his father. His father wanted him to go to medical school. Darwin had some issues with the first time they did surgery on an infant without anesthesia. He's like, this is not for me. I don't want to do this. He was going to go to school also to be a clergy in the Anglican Church. Not for me. So an opportunity came for him to get on a ship for the British government, or actually the king. They were mapping the coast of South America, and if you see on that map, through Australia and then back around, and they need a naturalist. So Darwin's like, yeah, sign me up. Problem is with Darwin, he had seasickness, and this voyage lasted 5 years. So we'll talk more about it, but often a lot of his data that he collected was that he would get off the boat and travel. And so he'd say, we'll see in 3 months, travel down the coast of South America, because he'd get seasick. Or if you ever had motion sickness, imagine being motion sick for 5 years. So there's the beagle. But anyways, so when we talk about natural selection, there's a couple things. Again, we're not going to focus on Darwin's voyages on the AP exam, but observation, there's got to be variation of population. So if you look at these two images, green and blue, what's the variation? You can pause this. It's the color. So that's your first observation. No two organisms are completely alike. And so if we look at the shells, you may want to think to yourself, well, what's different about them? Well, if you look at the shells, it's definitely the rings. What I'm calling about those rings is like the coloration there. So that's evidence for that observation. Observation 2, reproduction. Reproduction has to occur. The most fit organisms have to survive and reproduce. If you don't survive and reproduce, you're not evolutionarily successful. And so if we look here, observation, reproduction occurs. Overproduction. Not all living things survive, right? And so you try to produce more offspring than will survive. So this is overproduction. So that's a dandelion. All of those represent fertile seed. Inference, you infer something, right? Different than observation. Inference, I take my data and I can kind of make a statement. Differential fitness in the environment due to variation. So differential fitness means that some organisms are more fit than others. If we look at these two circles, the green and the blue, you can probably make a guess. I don't know why I use that word gander. Which one's more fit? Pause, think. Which one is it? The blue one. And the reason why the blue one's most fit is because it's leaving the most offspring. So and there's always going to be a struggle for existence, right? A struggle for existence. So if we look at this image here, we've got some bears. I think they're grizzlies because they got that hump right there on its back. And they're probably feeding on some salmon. Again, don't question me if I got the wrong bear. I apologize. But there's a struggle for existence. Some things are going to be better fit than others. Some are going to do a better job at struggling for existence, are going to survive. And so in actuality, there's a lot at play here in this image. The salmon are going upstream, right, to lay their eggs, to spawn. The bears are trying to catch their food, but also you don't think about often what bears do is when they eat those fish, they'll drag that carcass across the ground to another area, which also adds fertilizer and nutrients to the soil. So there is a struggle for existence. Inference 2, I'm going to kind of move my face down here. Over the span of geological time, billions of years, inheritance of adaptations will lead to the evolution of a population. So if we look at this population here, which ones are most fit? So if you want to pause this, the ones that are most fit are the blue because they left the most offspring. So some fundamental conclusions. If you're doing your own notes or whatever, I'd write this down. The first one, to develop the diversity of life seen on Earth, the Earth has to be incredibly old, which we'll talk about. The second conclusion, if organisms evolved from pre-existing organisms, then all organisms should share a universal common ancestor, which there is evidence for. And so when we're looking at evolutionary theory, these are your fundamental conclusions. Earth is old, common ancestor. All right, tree thinking, which we'll talk about. This is that idea of phylogenetic trees. We'll talk about phylogenetic trees, but this idea is that each branch represents a speciation event. And we'll get into this a little bit more later, into a later discussion. I'm just checking to see how far I got to go. All right. So these are things that are unsettled by Darwin: origin of life, origin of species, nature, variation, inheritance. So he did not have a conclusion about the origin of life. He did not have the conclusion of the origin of species, and he did not understand how nature, variation, inheritance. These would come later, but his basis for the fact that things change over time will eventually allow us to settle these questions. So let's talk about modern synthesis. So the modern synthesis is where we apply genetics to Darwin. Now, if you ever see a question in the AP exam where they're talking about Darwin, they're mentioning genetics, Darwin and Mendel lived at the same time. They did not share their data. Again, this is in the 1800s, right? Darwin died in 1882, so probably in the 1860s, whatever. They were not sharing information. So, but modern synthesis is how we connect Darwinian evolution to genetics and modern understanding of inheritance. So, where traits come from? Okay, so this is, oh, lights went off. Give me a second. And I'm back, and there's nothing I can do about it. So DNA to RNA to protein, that's your central dogma, and ultimately a trait, right? DNA, RNA to protein to your trait, and that's kind of where that process occurs. So we're going to see this quite often. Because once there's a change in the DNA, ultimately leads to change in the protein, can lead to a change in a trait. So variations come from mutation. Mutations are change in DNA sequence, happen spontaneously and unavoidable. Some, not all mutations are bad. Some mutations are good. And so when we're talking about mutations, mutations are the driving force in natural selection. Without mutation, mutations are about impossible to control. Well, I take that back. Now with CRISPR, who knows, we might be able to control them. Mutations create alleles. So alleles are different versions of a gene. So you have a trait, say height. You may have an allele for tall, capital T, and an allele for short, lowercase t. You have to understand in biology, though, it's not that simple. There are some clearly dominant recessive traits where it's a single allele, a little more complicated, but alleles, and we'll talk about change in allele frequencies. So evolution defined, put a star by this, but it's a change in allele frequencies over time. And so I'm going to move my mug up here. Here's our original population. We've got all these different colors. Initial frequency, I think, is 20, 20, 20. I know that bottom picture's cut off 20. Let me see if I can just scroll that up a little bit. 5 generations later, our frequency has changed. What I mean by frequency are these numbers. So we went from 20.2 to 0.4, 0.2 to 0.06, 0.2 to 0.2, 0.2 to 0.14, 0.2 to 0.2. So there was no change in the red population. There was no change in the blue. Well, excuse me, there was no change in the red. There was a change in the blue. 10 generations later, we can see that the allele frequency has changed. We've actually eliminated the yellow and the pink. So this is by definition a change in allele frequency, and we'll apply this later. So when we talk about modern synthesis, we can also talk about the finches. So the Galapagos finches, which we'll be talking about. So Grant, they did studies, and again, I'm checking out 3 more slides here, studied the finch population on an isolated island in the Galapagos. Islands are great. They're isolated. You're not going to have things like gene flow and a lot of new alleles entering a population. And so they did was they measured the beak dimensions. And so what they did was they found that the change in beak dimension fluctuated in the population based on precipitation and seed size. For natural selection to occur, you have to have a change in the environment. The environment is what is selecting the factor, right? And so if you have an environmental change, right, those organisms that are best adapted to that environmental change will survive. And so as we can see here, the large beak, right, it kind of fluctuated with the precipitation, which again on the bottom, during these different years, you can see when there was a change in precipitation. You're going to be watching a video. And so here's the misconception alert. Individuals evolve. They do not evolve. Populations evolve. All right, so that's a key point there. Populations evolve. Evolution is a population level phenomenon. Individuals do not evolve because they have to have reproduction. The evolution of a population emerges from individual fitness of members of that population. So it's the population driving evolution. As they survive and reproduce or not, the frequency of alleles in the next generations will change accordingly. So again, it's a change in allele frequency in a population, not an individual. So that was our first kind of lecture. I'm trying to keep it about 12 minutes. I know it's a lot to watch, but so we're gonna leave off here with little Eminem. So I'll be back here in a little bit with another presentation. This is me signing off from room 102 in the heart of Pittman Columbian. Have a great day, and I'll see you later. We gotta let Eminem play a little bit. All right, I'm off. See you later.